Sama. Assalamualaikum and good afternoon. Can anyone hear me?
Yes, I can hear.
All right. Thank you. Before we begin, let me check the three presenters here. Miss Chiam.
Yes, I'm here.
All right. Okay. The second presenter, Miss Nur Farhana. I think not here yet. Okay. Our invited speaker, Dr. Siti Maria, is here. Okay. I can see Miss Nur Farhana also here. Okay. I think without further ado, since everyone is here, I would like to read some announcement before we begin. All right. Because the presentation will be started at 2 p.m. Okay, so let me begin with some announcement. Okay, before we start the session, please check the pre-recorded video presentation and the presenter attendance. Blah blah blah. All right. Okay. Assalamualaikum Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon, ladies and gentlemen. All right. We are about to begin session parallel number 5, Nanofabrication and Characterizations. Okay. Please stand by. I would like to seek for your kind cooperation to avoid any virtual disturbance during live broadcast session. If you have any question, the conference resource personnel are ready to attend you at the reception desk. Okay, thank you for your kind cooperation and attention. Okay, we will start at 2 p.m., which is approximately in, according to my time, 6 minutes from now. All right, and my name is Nurul Izaila alias. I am a senior lecturer at University Technology Malaysia. So I will be the session chair for today. Okay, together with the session moderator, which are I think the IT personnel is Miss Nurul Hazirah Kamarudin and Miss Shabilah Sabari, and the evaluator are Dr. Yu Ming Chian and also Dr. Asmalina Muhammad Saad. I believe all of us are here today. Okay, I invite all of the invited speaker and also the presenter to request to share your audio and video now. Okay, you may click the button on top right. Okay, so okay, everyone is okay. All right. So ladies and gentlemen, the oral presentation will be evaluated for the awards under 2 categories. Best session presenter, that will receive the certificate for best presenter, and I will announce at the end of this session. For best presenter award, that offered prize money from 500 ringgit to 1,000 ringgit, trophy and award certificate. Okay, this will be announced during the closing ceremony. So I would like to seek for your kind cooperation to mute your microphone if you're not presenting, and to avoid any kind of virtual disturbance as possible. For those who intend to ask question to presenter, you can channel your question in the Q&A box. I will read it after every presentation. You can also request to share your audio and visual to ask your question in live mode. Okay, presenters are given 15 minutes of presentation and 5 minutes for Q&A session. Okay, whereas for the invited speaker are given 25 minutes for presentation and 5 minutes for the Q&A session. I will remind the presenter to end the presentation 2 minutes before the presentation session ends. I will stop the presentation session when the session has exceeded the 5 minutes allowed. IT personnel, can we take picture? Ready to take picture now? I can't hear you.
Sure, Doctor.
All right. Okay. So since everyone are here now, okay. Before we start this parallel session, I would appreciate if everybody can turn on the camera for a photo session. Okay, IT personnel will take a screenshot. Tell us when you're ready. IT personnel.
Okay, wait. 1, 2, 3. Oh, wait. There's
I think Dr. Asmalina didn't turn on your video. Dr. Asmalina, is it possible if you can turn on your video? All right. No, where is Dr. Asmalina?
wait.
It's okay. You just proceed. Sorry.
All right. Okay. Okay, sure.
1, 2, 3. Okay. One more time, freestyle. 1, 2, 3. Okay.
All right.
Thank you.
According to my time now is 1:59. The first presenter, are you ready? Shall we begin now?
Yes. So
All right.
I shall share my screen now.
Yes, please. Okay, without further delay, you will be hearing a presentation from the first presenter, Ms. Chiam Sing Ling. Okay, her presentation entitled Facile One-Step Synthesis of Mangan Oxide, is it?
Manganese oxide.
Okay, manganese oxides, nanostructure using rapid heating method for rhodamine B dye removal. So the floor is yours, Miss Cham.
Can you all see my screen actually?
Yes, I can see your screen. Okay.
Good afternoon, everyone. My name is Cham Sin Ling. I'm from University Science Malaysia. So today I'm going to present my project entitled Synthesis of Manganese Oxide Particles via One-Step Localized Heating Method as Catalyst for Dye Degradation. First of all, I would like to start with a little research background of my study. Water pollution can come from a number of different sources. The four main types of water pollutions are microplastic, suspended matter, microbiology, and chemical, which is the main focus of this study. Industrial and agricultural work involve the use of many different chemicals that can run out into water and pollute it if no proper treatment have been done. So example of chemical pollutions such as metal ion, pesticides, petroleum, and dye. Dye, a type of chemical pollution, is a vital chemical used in several industries, such as those involved in producing fabric, food, furniture, and paint. So during a dyeing process, up to 50% of the initial dye concentration will remain in the spent dye bath, which will result in color effluent. Therefore, we need effective wastewater treatment technology to support the high increase in the industrial dye discharge. General, in the dye removal method, it includes primary, secondary, and tertiary method. Primary method can efficiently decolorize the insoluble dye, but it is not very effective in reductions of soluble dye. Secondary treatment include aerobic and anaerobic process. It is used as a typical treatment nowadays. However, aerobic treatment is not efficient in the removal of azo dye. Tertiary treatment is more significant than primary and secondary treatment because it enhances effluent treatment. Dye wastewater contain various types of hazardous. Usually, they require more advanced treatment method to treat more particulate pollutants. So, example of tertiary methods such as membrane technique, advanced oxidation process, ion exchange, and absorption. Among advanced oxidation process has been reported as one of the efficient procedure. It is based on highly reactive radicals species leading to the degradations of the target pollutant non-selectively. The merits of advanced oxidation process include eco-friendly nature, able to achieve complete degradation, low cost, and increase the reusability of water. The common AOP candidates are titanium oxide and zinc oxide. They show good stability and excellent dye degradation properties under ultraviolet light. However, due to their wide band gap, they have limited activity under visible light exposure. In fact, as we all know, UV light only stands a small portion of the spot spectrum, which is around 4%. As you can see from the graph here, under visible light conditions, zinc oxide nanoparticles and titanium oxide nanoparticles are only able to degrade less than 20% of the dye. So to improve their visible light absorption, modifications on the structure and compositions of titanium oxide and zinc oxide has been carried out throughout this year using doppling, coupling, and etc. Besides, as an alternative, we can use the manganese oxide, which is a narrow bandgap semiconductor. The bandgap of manganese oxide is in the range of 1 to 2 electron volt, which is able to be activated by visible light. Our preliminary result shows that manganese oxide particles show selective removal on silver ion under visible light. It also shows selective removals of copper-2 ions under visible lights. Besides, manganese oxide also has been widely used in energy storage device, therapeutic activity, and sensor due to their attractive properties such as stability, relatively cheap, and safe. For dye removal, manganese oxide poses various redox activities, low toxicity, and abundancy. Those make it attractive in wastewater treatment. Commonly, manganese oxide are synthesized using hydrothermal and sol-gel method, as their process of synthesis are simple, easy to repeat, and the size and morphology can be easily tailored by changing the reaction parameter. For this method, the heat generated by the heating coil are transferred externally from the reactor system to the precursor solution. Hence, this method usually requires relatively long synthesis duration, high usage of electrical energy. So they are not efficient in terms of energy and time, as most of the heat are lost during the process. This becomes the main drawback for practical application, as mass production at low cost of synthesis is required. In this study, we introduced the use of localized heating method. It is a rapid synthesis method using the passage of electric current to generate heat and transfer directly to the target solution. First, we shows the price comparison among three methods, which are hydrothermal, sol-gel, and localized heating. As you can see, the cost of apparatus for hydrothermal is around 6,000 Malaysia ringgit, including a Teflon and oven. For sol-gel is around 4,000 Malaysia ringgit, whereas for localized heating, we only need 2,000 Malaysia ringgit to buy an AC regulator. Next, the total electrical cost per experiment for localized heating is the lowest among these three methods to synthesize the same amount of the manganese oxide. So, how this localized method actually works. The picture on the left is the actual photo for localized heating setup, and the picture on the right hand side shows the schematic diagram for the localized heating. First, the precursor solution is prepared. Then a benchtop power regulator, which is an AC regulator, will use to pass the electric current to the wire. So since the wire is submerged in the precursor solution, the heat is transferred directly and rapidly into the target solution. By this, the heat loss can be minimized. In this study, the particles formed after 10 and 50 minutes will be collected for characterization and application. Overall, The advantages of this method include short synthesis duration, low power consumption, energy preserve, low synthesis cost, and it is possible to be scaled up. So as mentioned, the particles collected after 10 and 15 minutes will be sent for XRD, FESAM, and TM. Then for application, they will be tested for the degradations of the RHB dye. So here the result of this study. This figure shows the XRD profile for the particle synthesis at 10 and 15 minutes. So both profile actually show similar diffraction pattern where they have 5 broad peaks, which is correspond to the crystal plane of MnO2. Besides, both profile display broad diffraction peak. This suggests that the manganese oxide particles that is synthesis is amorphous. Here is the morphologies of the manganese oxide particle synthesis at 10 minutes and 15 minutes. So in general, they possess different morphology. At 10 minutes, we can see that hierarchy flower-like structure were formed. When we're looking closer, we can see that these flower-like particles were made up from assembly of thin intersected nanosheets. Besides, we can also observe some tiny particles found deposited on the MnO2 nanoflower as highlighted in yellow color. By increasing the heating durations to 15 minutes, agglomerated structure were observed over the surface of the MnO2 nanoflowers. Next, this is the TM image of the MnO2 particle synthesis at 10 minutes. It composed of wrinkled and intersected nanosheets that self-assembly and finally grow in all directions to produce MnO2 nanoflowers. From HRTM, we can see that there is short and non-continuous lattice fringes distributed all over the structure, as highlighted in yellow. Besides, most of the region lack of lattice fringes, which indicating that the MnO2 nanoflowers are amorphous. This observation is aligned with our XRD analysis earlier. Next, the SAED pattern also exhibit diffuse ring, again indicating the amorphous characteristic of MnO2. So combining the characterization result, a growth mechanism for the MnO2 particles synthesized using localized heating method is proposed. At time equals to 0 minutes, since there is no electrical supply, no heat will generated from the wire. So the temperature of the wire and solution remain at room temperature. At this time, no manganese oxide particle were synthesized. After switching for 10 minutes, the temperature of the wire reached 85 degrees Celsius, where the precursor solution reached around 80 degrees Celsius. This observation actually suggests that the heat transfer rapidly into the precursor solution through the localized heating method. So this is explainable because the localized heating method allows the heat transfer directly and constantly into the precursor solution. So this offers more efficient energy transfer and thus high heating rate. So this temperature is enough to or sufficient to initiate the redox reactions between the potassium manganese and manganese sulfate. So according to classic nucleation theory, under high heating rate, a burst of nucleation reaction will be occur in a short period of time. Therefore, we will have a lot of MnO2 nuclei. So these nuclei will self-assembly and grow into nanoflowers. Besides, under high rapid heating nucleation or under high rapid heating rate condition, secondary nucleation will occur. Therefore, we observe some nanoparticle deposited on the nanoflowers. By prolonging the reaction to 50 minutes, most of the precursor was depleted, so a slower nucleation rate was observed. However, under uniform heating temperature, oswald ripening tend to occur, where the small crystal will redeposited onto larger crystal over time. Therefore, we observe an agglomerated structure at time of 50 minutes. So the catalytic activity of MnO2 particles were investigated by assessing their removal efficiency towards RHB dye. So both the characteristic peak decrease with time. The characteristic peak of MnO2 particle synthesis at 10 minutes reduced at a faster rate if compared to that at the 15 minutes. We can see that the relatively intensity of the absorption peak of MnO2 synthesis at 10 minutes nearly vanished after 20 minutes of the reaction time. So the removal efficiency is quantified in this plot. The degradation efficiency of MnO2 particle synthesis at 10 minutes are 99%, whereas for 15 minutes is only 17%. So the degradation process actually follows pseudo first order kinetic. The efficiency of MnO2 synthesis at 10 minutes is actually 60 times higher than that of synthesis at 50 minutes. Besides, the MnO2 particles at 10 minutes can remain their catalytic activity up to 70% after being reused for 5 cycles. When we compare it with commercial titanium oxide and zinc oxide, we can see that actually our synthesized MnO2 outperform both the titanium oxide and zinc oxide, which is the commonly used AOP candidate. Besides, scavenger tests will also carry out to determine the main reactive species involved in the degradations of the RHB dye by our MnO2. From the test, we can find out that hydroxyl radical were the major reactive species, while the superoxide and radical and ethanol are minor reactive species. So combining all the results, the mechanism of dye removal is proposed. The crystal defect in the amorphous structure of MnO2 act as an electron donor. So the electron will react with the oxygen species through a series of oxidation process to produce to hydrogen peroxide. So the manganese ion in MnO2 will catalyze the reaction of hydrogen peroxide to produce the hydroxyl radical. As we all know, hydroxyl radical are very effective reactive species which are able to degrade the dye into smaller molecules. So the mechanism is proposed to be oxidative degradation, where the disintegration of RHB molecule was by the action of oxygen. So as a recap, this study shows the synthesis of manganese oxide using localized heating. Then the process only requires 10 minutes. Then the synthesized MnO2 is able to degrade the RHB dye in 20 minutes, where the performance is able to remain 70% after 5 cycles. And it also outperformed the commercial titanium oxide and zinc oxide. So as a highlight, we can say that this study shows a fast, versatile, and efficient method in synthesis of MnO2 in 3D nanoflower morphology, and it can be a promising visible light active photocatalyst. Thank you for your time.
Thank you very much, Ms. Chiam Sin Ling, for addressing a very interesting topic and nice presentation. So, ladies and gentlemen, now we open the floor for Q&A. All right. Please mention your name before addressing your question, or you can drop a question in the Q&A box. All right. If no question, Ms. Cham, I have 2 questions. Okay. You for the localized heating method. Okay. So you did on 10 minutes heating and 15 minutes heating. How about less than 10 minutes? In between 0 to 10 minutes, you able to get the synthesis, the morphologies? Any morphologies can be synthesized within that time, maybe 5 minutes?
Okay, if let's say if 5 minutes we are able to get the powder, but from the XRD analysis we couldn't get any peak which is related to manganese oxide. Therefore, we assume that at 5 minute time is not efficient or sufficient to synthesize MnO2 particles. Therefore, we set it at 10 minutes and 50 minutes.
I see. So between 10 minutes and 15 minutes,
yes.
Between 10 minutes and 15 minutes, which one is the best? I mean, to get the most successful morphologies?
10 minutes, because if 50 minutes, we can see the structure is already agglomerate. And then when we go for the practical application, which is dye degradation, we found out that the degradation efficiency actually is very worse for the 50 minutes one if compared to that synthesis at 10 minutes.
I see. Okay, my second question, if I'm not mistaken from your presentation just now, the other AOP candidate were titanium oxide and zinc oxide, right?
Yes.
Yeah.
Sorry.
So the one that you compared the intensity. Hello?
Hello.
Yes,
Hi.
can you hear me?
Yes, now can.
Yeah. Okay. All right. So when you compare your result with the other AOP candidate, if I'm not mistaken, zinc oxide and titanium oxide.
Yes.
Okay. That one was your experimental, or you compared with other researcher result?
No, this is my experimental. I use the commercially obtained titanium oxide and zinc oxide and then I compare it. I did also mention the
I
number on my
see.
presentation slide.
I see. Okay. So you found out that the best candidate is manganese oxide,
Yes, if under visible light condition.
right? Okay. Okay. All right. Okay. Thank you. Thank you, Miss Chiam Sin Ling, for your presentation and answers. I just want to ask the IT personnel, is my voice is breaking up?
No, it's fine for me.
Okay.
No. All right. All right. Okay. Okay. Thank you. All right.
Okay, thank
So
you.
now we move. Okay. Thank you. Thank you, Miss Chiam. Now we move to the next presenter. Okay. We have here. Sorry. Okay. Miss Nur Farhana binti Shahrul Azhar. She will be presenting her work entitled Temperature Dependent Photoluminescence of Core KDSE Quantum Dots. Miss Nur Farhana, are you ready? You can start sharing your slides presentation.
Okay, good day. Do you hear my voice?
Yes, I can hear.
Okay, I will share the recorded video.
Oh, okay. All right. Okay.
Okay. Can you see the video?
Yes, can see. Okay, you may begin the presentation now. Thank you.
Alright. Assalamualaikum and good day. I am Nur Farhana.
It is quite slow from my side. Can you make it loud, a little bit louder? Can you increase the volume?
This is the highest volume. I'm not sure why when I share it, the video, the sound of the video
It's
become.
okay. It's okay.
Miss
It's
Fana,
okay. You,
do you want me to help you to share the video?
Yes. Thank you. Thank you.
all right. Maybe you can stop sharing and let the IT personnel share the video. Thank you, Miss Farhana.
Thank you. Assalamualaikum and good day.
Okay.
I'm Morphologies from University Kuala Lumpur, British Malaysia Institute. Today, I will present our research title, Temperature-Dependent Photoluminescence of Core Cadmium Selenide Quantum Dots. Nowadays, in this nanotechnology field, semiconductor quantum dots are the most explored by the researchers in these last 2 decades because of its unique behavior, size-dependent optical, unique electrical and magnetic properties, size-tunable, luminescent, and also broad absorption spectra. Through chemical synthesis, the size and shape of quantum dots can be controlled, which eventually allows to control the material bandgap. Cadmium selenide quantum dots is one of semiconductor quantum dots. Typically, the size range is between 1 to 10 nanometers. In the periodic table, cadmium selenide comprise an element in column 2 and 6. There are two types of cadmium selenide crystalline form. First, the woodside, also known as hexagonal. Second, the rock salt, also known as cubic. The cubic crystalline form also can be converted into hexagonal form by heating the sample with temperature 350 degrees to 440 degrees. In quantum dots, cadmium selenide quantum dots are well known due to their good quantum yield, high luminescence, high photostability, and tunable emission spectra. With this unique property, it is mainly used as purpose in biomedical imaging, polymer-based photovoltaic cells, amplifier, low threshold laser, quantum LED, and others. Two main objectives in this research: first, to study an optical characterization of cadmium selenide quantum dots based on temperature-dependent PR spectra. Second, to understand radiative and non-radiative emission process with respect to temperature changes. Photoluminescence or PL technique is one of the widely used methods to investigate optical and physical behavior. This is because of their non-destructive nature. In this study, PL intensity, PL peak position, and full width half maximum are the optical characterization of cadmium selenide quantum dots which have been investigated at temperatures 80 Kelvin to 300 Kelvin. By measuring the PL spectra based on the temperature dependence, it allows to study the radiative and non-radiative emission process. As for the methodology, first, we use modified kinetic dose method for the synthesis of the sample. By broadcasting the cadmium selenide quantum dots in solution onto the quartz substrates, thin film for measurement is obtained. The sample then loaded into a brisk probe of 3 and 77K nitrogen gas cryostat with optical access. Next is the PL temperature-dependent measurement setup. The measurement setup is shown in the figure. The cadmium selenide was excited by using unpolarized 405 nanometer laser diode excitation onto the quartz substrates, and then PL spectra were gained. After gathering the emitted PL from the cadmium selenide film series, and collimated onto the cryostat window before being focused onto the monochromated slits, and then distinguished by the silicon photodiode. Long pass filter will eliminate any 405 nanometer analog detection is allowed due to the modulation of laser beam. Thus, all the PS spectra been rectified for the system spectral response. As for the result, this is the figure for the temperature dependent of cadmium selenide quantum dots PL spectra from temperature at 80 Kelvin to 300 Kelvin. We can see there are two peaks in the figure, first peak and second peak. This spectrum shows by model distribution Gauss behavior, displaying homogeneous broadening. Due to the well distribution of cadmium selenide quantum dots diameter approximately around 4.5 nanometer within the sample. The first PL peak is centered at 1.9 electron volt, while at the second peak centered at 2.4 electron volt. For the first PL peak, as temperature decreases from 300K to 200K, a redshift of PL peak position is observed. Then it is shifted when the temperature decreases from 200K to 80K. PL intensity for each spectrum reduces with increasing temperature from 80K to 300K. For the second PL peak, a blue shift is observed, but only with a low rate, and there is no significant change is observed on the PL intensity for each spectrum. For the PL spectra, we can observe it is almost identical for both spectra. However, upon close inspection, there is a reduction in width as temperature decreases. Next is the result of temperature dependence on cadmium selenide quantum dots PL peak position. This is the figure PL peak position versus the temperature. The data are fitted using two fitting. First, the Varshni fitting. Second, the Bose-Einstein fitting. Varshni equation is acknowledged to yield wide variation in thermal parameter for the same material. This indicating the energy gap at 0 Kelvin. This is the temperature coefficient. This parameter is related to the by temperature. From the figure, generally, we can observe as temperature increase, the PL peak position decrease. However, at first PL peak, fitting only can be done at temperature range 200K to 80K due to the nature of blue shade peak position, which is same as previous reported by others. At 200K to 300K, redshift behavior is unexpected due to the increased temperature. cause high vibration energy within quantum dot atom, and this led to lower bandgap behavior. As an alternative to provide more accurate and precise result, Einstein temperature fitting is used, as the error return is much smaller compared to the Barney fitting. This represents the strength of electron average phonon interaction. This is the Einstein temperature. This parameter is correspond to the acoustic phonon, which contribute to the bandgap redshift. When the Einstein temperature value is lower than the optical or LO phonon energy, acoustic phonon will highly contribute to narrowing the bandgap because of the electron-phonon interaction. From this study, it is expected that the acoustic and LO phonon is highly contribute toward the quantum dot bandgap shrinkage, as our Einstein temperature recorded is lower than LO phonon for the first PLP. However, for the second PLP, the parameter recorded is far from previously reported. This is the figure for full width half maximum, or we call it as FWHM. From the figure, FWHM increase as temperature increase. It is representing broadening of emission peak as temperature rise. FWHM fitting is used in this data. Acoustic phonon and LO phonon are the factors which cause bandgap broadening in semiconductor quantum dots. Acoustic phonon contribute at low temperature, LO phonon contribute at high temperature. The broadening of lifespan that corresponds to the elevating of electron phonon scattering rate has causing the FWHM widen as temperature rise. The quantum confinement has caused the exciton acoustic phonon coupling increase and the exciton LO phonon coupling constant reduced to 25.6 millielectron volt with respect to cadmium selenide quantum dots reported. Using 25.6 millielectron volt LO phonon energy, it showed that our sample has slight difference with previous reported temperature effect toward cadmium selenide quantum dots PL emission broadening for the first PLP. Our fitting shows strong inhomogeneous broadening and agreeable PLO. This showed that the exciton LO phonon coupling mainly contributed to the homogeneous line width for quantum dots for this particular sample. The single molecule absorption line width becomes broad at high temperature due to the exciton phonon coupling is stronger. At second PLP, FWHM fitting shows low on all parameters at the same value of LO phonon energy, 25.6 millielectron volt. This might indicate as temperature decrease, small phonon activity reported, and also indicate second PLP emission may not be contributed by the radiative emission process. Next, the result for temperature dependence on cadmium selenide's quantum dots, PLP intensity, and PLP integrated intensity. A simple linear fitting is used for further analysis for both speed. However, both fitting can only be recorded for first PL compared to second PLP. For figure PL intensity versus temperature, at first peak, PL intensity decreased as temperature increased. Yet, at the second peak, the pattern observed is random. It also can be seen at temperature 220 Kelvin. There is a crossover between first PL intensity and second PL intensity. For figure PL integrated intensity versus temperature, the trend is approximately similar to the figure PL intensity versus temperature. The PS spectra of cadmium selenide quantum dots will investigate to understand the radiative and non-radiative emission process with respect to temperature changes. Generally, at high temperature, a semiconductor demonstrates low PL intensity compared at low temperature. This is because an increase in non-radiative phonon interactions. As the temperature increases, numerous free excitons are released from the bound state, which cause the emission to gradually disappear. For the second peak, the PL intensity is inconsistent, and reduction of PL intensity at low temperature is resulting of the carrier trapping in defect state, which at low temperature thermalization can occur. These trapped states are commonly known as PL spectrums low energy solvent. This is the illustration of energy level for cadmium selenide quantum dots at two different regions, EVA and EVC, represent the main radiative emission process. EVB and EVD represent non-radiative emission process. Delta A and delta B represent the difference between energy level from ground state to excited state. This suggests that the radiative emission originates at first PLP, while the second PLP is from non-radiative emission. As normally reported, temperature decreased as temperature increased. This is because of the amplitude of atomic vibration increased and led into larger interatomic spacing. This behavior can be observed in the cadmium selenide quantum dot's first PLP, which decreased as temperature reached 300 K. But for the second PLP, the nature is still unclear. Thus, we suspect that it is originated from the surface trap state. At high temperature, non-radiative process is dominant, and more phonons are released. It is suspected that both emission process come from non-radiative recombination that lead to emission from crack state to ground state of quantum dots. At high temperature, most emission of quantum dots is coming from non-radiative, involving phonon interaction. As temperature reduces, the phonon interaction will become weak, and radiative process will dominate the PL process within quantum dots. In the illustration, we suspected that the phonon interaction play an important role in transferring electron from excited state quantum dots to the trapped state. As at high temperature, delta B shows much wider gap between quantum dots excited state with trapped state. However, at this temperature region, high phonon interaction will contribute to the non-radiative emission process, which lead to a high intensity in the second peak compared to the first peak, as shown in the figure PL intensity versus temperature before. Our finding also supported based on FWM fitting or excited LO phonon coupling, where strong optical phonon interaction compared to others. As temperature decreases, the bandgap of quantum dots is expected to expand closer to the trap state energy level, thus energy difference delta A becomes smaller. The optical phonon interaction also expected to reduce. This computation between the radiative process first peak and non-radiative process second peak can be observed within the sample where at 220 K, where the PL intensity for both PL peaks overlap to each other, suggesting the change in the dominant emission process. Further experiments need to be conducted to support such claims through temperature-dependent absorption and PL lifetime measurement. As conclusion, the cadmium selenide quantum dot through modified kinetic group synthesis method have been investigated its temperature-dependent PL behavior. The cadmium selenide quantum dot's band gap is estimated at 1.9 electron volt, with suspected size distribution around 4.5 nanometer. We believe that the second peak to have a trapped state at the surface of quantum dots. There were two different processes involved. At low temperature state, radiative process is dominant. At high temperature state, non-radiative process is dominant. We also found that the exciton longitudinal optical ELO value is 25.6 milli-electron volts, which is similar reported by others. This study gives us highlight of the exchange process, radiative and non-radiative emission process, which may contribute to more future experiments. Last but not least, we would like to thank University Kuala Lumpur for the financial support and also to Dr. Alif Razwan bin Muhammad Razi for the meaningful and effective discussion. Thank you.
Thank you very much, Ms. Nur Fahana, for a very clear and nice presentation. All right, so I open the floor for Q&A. If you have any question, you can drop in the Q&A chat box, and you can also you can turn on your mic and voice out your question if you have any. Okay, if no, then I have question, Ms. Nurhana. So I can see that from the KDSE quantum dots PL just now with a different temperature, so you're able to get the very high peak for the first peak, and then it dropped, and it dropped the intensity peak drop until you get the second peak. So why is that the second peak is much lower than the first peak?
Thank you. Thank you for the question. We assume that the second peak maybe will is the trap state that that occur surrounding the cadmium selenide quantum dots.
I see. Is it interface trap at the inside the material or at the surface of the material?
At the surface of the material. But
I see.
we need
Can
further experiment to support the claim lah.
So is the trap is permanent trap or it will be disappear for a long time release? What do you think?
I'm not sure about that, but based on the time taken from 80K to 300K, the temperature there are still value for the second peak.
I see. I see. Okay. So is there any way or chance to although to improve the second peak from your opinion maybe?
My opinion, maybe we can do surface modification to reduce the second peak value.
I see. I see. All right. Okay. Thank you very much, Miss Nur Fahana, for nice presentation and also for the answers. All right. So thank you. So now we move along to the next presenter. Actually, the next presenter is our invited speaker. Okay, please welcome Dr. Siti Maria Muhammad Yassin. Okay, her presentation entitled Strength of Kenaf or Glass Fiber Reinforced Epoxy GRE Composite Lab Joint. Dr. Siti Maria, are you ready? You have 25 minutes of presentation. The floor is yours, Doctor.
I'm trying to be ready, okay?
All right, okay, the floor is yours, Doctor.
Okay, thank you. Okay, I share my screen.
Yes, please.
Is there my slide presentation there?
Yes. No. Okay, can you try once again? Yeah, this one.
Do you
All
see?
right. Yes, very clear.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Good evening, everyone. I am Siti Maria binti Muhammad Yassin. I am postdoctoral researcher at my institution, which is University Malaysia Perlis, situated at Perlis, Malaysia, north of Peninsular Malaysia. Today, I want to bring my title about strength of kenaf or glass fiber reinforced epoxy composite lap joint. For audience information, I am very new for this project, which is I started this project for 5 to 6 months ago, and this project is also the new of in this my institution, and I acknowledge that other university from other university such as USM and UNIKL start earlier about this natural fiber of kenaf to be as a composite material reinforcement. Okay, this one is for the introduction of my project. I give the briefly information about the synthetic fiber first. The synthetic fibers are manufactured from a string of combination of small units of chemical substance, and these are examples of several artificial fibers, which are carbon, basalt, glass, and Kevlar fibers. And The synthetic fibers are more durable. Uh, uh, According to, it is not wrinkle easily. It is also elastic, which is it cannot be easily stretched out, and also strong, which is it can sustain the heavy load, and also cheap compared to the natural fiber. And this slide briefly about natural fibers. This slide, some natural fiber will be shown here, which is natural fibers mostly derived from trees and plants such as flax, hemp, kenaf, jute, henequin, coir, wood, corn, and pineapple, which is they considered to be environmentally friendly. Natural fibers have become the raw material which is used by many industries, including aerospace, automotive, marine, military, as well as for defense industries. Okay, according to finding, natural fibers were utilized more than 3,000 years ago as a reinforcement for materials in many countries. And most research nowadays emphasize the development of a new natural fiber based composite, which is exhibit the best performance in terms of mechanical properties. For example, tensile, flexural, and as well as impact strength. Okay, the use of natural fibers as a renewable material reduce the use of synthetic fiber, which does contribute to preserving natural fossil resources. We go for the next slide. The natural fiber have been selected in my project is kenaf fiber. The kenaf, or the scientific name for the kenaf fiber, is Hibiscus cannabinus, which is this plant is an annual hibiscus plant originated from West Africa and spread to Asia via Egypt, and it is available in Malaysia, in Indonesia, Thailand, Vietnam, and also United States. Kenaf plants grow quickly and is a renewable resource, and it may guarantee a continuous supply. Kenaf fiber provide potential plants to replace tobacco plantation and encourage the growth of agricultural-based economies. And then the properties of kenaf fiber reinforced composite can be improved by hybridized with high-strength synthetic fiber. And various uses of kenaf, such as we can make rope, furniture, roofing, soundproofing, textile, bicycle frames, softboard, fishing rod, and etc. And the second material that have been chosen in my project is a synthetic fiber, that is a glass fiber. The glass fiber is used as a reinforcing agent for many polymer products to form durable, strong, and lightweight materials. This is according to their special properties that resistant to fire, which is the synthetic fiber made from inorganic material, making the product non-combustible. And also it has properties as a good chemical resistant, which is highly resistant to the attack by most chemical, and also durability properties, which is not prone to sunlight, fungi, and also bacteria. How about the hybridization among kenaf and glass fiber, which is the natural fiber and synthetic fiber. Okay, over the past decade, there has been an increased demand for green or natural fiber reinforced composite. The new material composite become lightweight, can enhance mechanical properties, and is free from hazard and low cost. One good thing with hybrid composite is that advantage of other fibers can overcome the disadvantages of one of the fiber used in the composite. The formation of hybrid composite offer excellent mechanical properties compared to single-use natural fibers as a reinforcing agent. The capability of hybrid composite make it possible to form fibers that can be used in multiple applications.
I'm sorry, is it my side? I lost the connection, or
Me too.
okay? So we lost Dr. Siti. Is she still here, Dr. Siti Maria? I cannot see.
Um,
And I think not here from the list.
yes.
I see. I think maybe we can play the recorded video. While playing the recorded video, maybe IT personnel can reach Dr. Siti Maria.
But we don't have her
I see.
pre-recorded, huh?
I see. All right. It's okay. We have some more time actually, like 15 minutes more. Maybe IT personnel can reach Dr. Siti Maria by calling her, maybe.
Okay, sure.
All right. Thank you. I think we lost Dr. Siti Maria. Okay. All right. since her allocation time given to her is actually about 25 minutes. Okay, now we have 11 minutes left. I think we shall wait for her. Maybe she lost her connection and right now trying to get back to the hop-in. So let's just wait for her a few more minutes. Thank you everyone for your patience. Thank you for your patience, everyone. Okay, we shall wait for 2 more minutes. Okay, I think it is fair if we wait for her until her allocation time given, right? So please do not leave, especially the presenter. We will be announcing the best presenter award after this. Thank you. Thank you everyone for your patience. All right, I think since Dr. Siti Maria cannot be reached, okay, either through phone call or message. All right, I think I shall end the session, okay, without, okay. Okay, now I am very honored to announce the best presenter for session nanofabrication and characterization. So the best presenter for this session, congratulations to Miss Chiam Sing Ling. Congratulations, Miss Chiam Ching Ling. All right.
Thank you. Thank you.
Okay.
So you
Thank you very much. So I think they will announce for the best presenter award towards the end during the closing ceremony. Okay. So
Okay.
now we reach at the end of this session. Thank you very much for your patience. Thank you for your participation. So on behalf of MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill up the feedback form as given by the session moderator in the chat box. So you are invited to join
我得到最 best presenter 哦。
the rest of the event, okay, the closing ceremony after this. Okay, hope to see you again. Thank you very much
然后
all.
他已经关掉了。等一下 ，Congrats Miss Cindy。
So Miss Chiam is so excited. All right. Okay, thank you all. Thank you, Miss Shabila.
Thank you, Doctor.
All right, okay.
Thank you.
Thank you, everyone. So the closing ceremony will begin at what time? Oh, the closing ceremony at 4. Okay.